Okay, we're going to start into chapter 6 on digital modes. This is a slide out of the ARRL manual. We're going to touch on some digital definitions, some codes and protocols. In my opinion, some of the protocols that they're presenting are a little outdated, um, but they're not incorrect. So we'll touch on those just so you're familiar with them. Um, some rules for digital modes and digital operating procedures in receiving and transmitting digital signals. So what we're going to start with um, are some general data transmission concepts. These aren't unique to amateur radio, but if you've worked at any level of involvement with digital systems, you might in computers, you might be aware of some of these. But we're just going to start and give some general overall descriptions of how some things work. So we're going to touch on digital data in general, take a look at the difference between parallel data transmission and serial, the difference between baud rate and bit rate, because you'll hear both of them as you go through, particularly if you're looking to buy a piece of equipment or use a particular protocol or mode. Uh, you need to kind of be aware of what the difference between the baud rate and the bit rate is. Um, Error detection and correction, and it's probably just because I'm a nerd, but I really think that's pretty neat. We'll get into some of the different ways um, that when you're transmitting and receiving digital data, the software can actually detect errors in the data and then make corrections to give you more reliability of signal. Of course, it's like everything else, there's a trade-off between speed and cost and accuracy and all that. We'll discuss that a little bit when we get there. And then the amateur radio modes, there's a lot of different modes, probably more modes than you can count on using some of these digital techniques, but there are some that are pretty dominant, and you'll probably want to give them a shot and see how they work out. And hopefully, it's a Sunday afternoon. The band's not real busy, but when we get through the academic part of this, we'll jump over to my radio and see what we can see on some of these digital bands. And then finally, transceiver duty cycle. And where that comes in is that we're concerned about duty cycle on the transceiver because the longer the transceiver is on at some power setting, the more heat that's generated, the more the radio heats up. So we have to be aware of the different duty cycles for some of these different modes, because they tend to run at 100% duty cycle, and that can have implications on your radio. So you just need to be aware of it, and then you can make adjustments accordingly to protect your equipment. So when we talk about digital, or another word for it is binary, meaning two states, excuse me, it's information that has either an on and an off, a high level, a low level, a dit and a da, a 1 and a 0. So there's only two possible states for the signal to be, either high or low. And this is an example of if this was time, if this is a graph with time, and you're sitting here and you're looking at this data as it's running. Let's start down at this end. Say we're here at time 0, and then this signal starts coming in. This is a low level, so that's a 0, and that's a 1, and that's a 0, and that's a 0, and that's a 1, that's a 1, 0, 0. But there's obviously a time base to it, so that when you're looking for the signal, you know when the signal period is. So it's either a 0 or a 1. And then 1 bit is considered this width. It would be where the transition would be in the center. So this signal's 1 bit wide, but the bit distance is here, bit time, I should say. So it's just the strings of ones and zeros. And depending on what the ones and zeros are, depends on the information you're trying to send and a bunch of other things. So that was that's serial data transfer. It takes a pair of wires or some sort of medium that you can send to strings of ones and zeros. There's also parallel data transmission techniques that can be used, and one common one is an 8-bit parallel combination where the sender has 8 lines going to the receiver, and these can all be zeros or ones, so you can transfer 8 times the information at the same time that we were doing 1 times the information in serial. So this is much faster. The cost is it's much more expensive to convey an 8-line data channel from the sender to receiver. So you see this a lot in close-up peripherals and oops, I accidentally muted myself. So this was pretty common, especially in the earlier PCs where you would use an 8-bit printer cable so it could transmit more data from the computer to the printer in the time, because at that time the serial data rates weren't necessarily high enough to have effective printers, for example, if you were doing it serially. Now the data rates are high enough you can do a serial printer on a USB line with no problem. Okay, now we'll take a look at how serial data transmission operates. And this just as an amateur radio. You'll find this if you have your home computer on the internet and there's a server you're going to get a web page. If you have a home local area network, if you're on a wide area network in business, they all pretty much follow this same type of structure, where the sender has some digital data they want to send. And it could be anything. It could be text, it could be pictures, whatever, anything that can be represented with ones and zeros. And the way it'll work is that there'll be an agreed to mode that's being used in this data transfer. So the sender will have an encoder that'll take this string of digital data and convert it in a format that is known by the receiver that has a matched decoder. So you can take the digital data, encode it, transmit it over the medium, and that medium could be a wireless network, or Wi-Fi type network. It could be an Ethernet network. A lot of different ways to do it. It could be the radio frequency on an HF radio or VHF, UHF radio, and then the receiver in some fashion receives that information, decodes it, and then they get the same information that was sent, which is the point of all the transmission. You want to get accurate information from one station to another. Okay, is that pretty straightforward then?
So far, so good.
Okay. And then we looked at this. I can't remember if it was earlier in this session or back in the technician session. But this was just showing ways that digital data transmission could be used in a VHF, UHF digital mode voice application, where you have a handheld or some other transmitting station, a repeater receiving it and transmitting the information either through the radio waves or over the internet with some sort of voice over internet protocol. And then it can go to another computer that's driving another repeater and then to the intended audience. So it's that, if you look at it, that's the same structure we looked at here, where the encoding and decoding for this application would be the distinction of a mode like D-Star, DMR, or Fusion, whatever other ones might be available. But they all have the agreed to encoder and decoder operations, so that the data can be received regardless of the medium that was used to transmit it. Then they run into bit rate and baud rate. It's fairly simple. The bit rate's the number of ones and zeros transmitted per second, and that makes sense. But then the baud rate can change depending on the types of characters you use. So some character sets may only use 3 or 4. If, let's say, 4 if you're just transmitting hexadecimal. Some could use 5, 6, 7, 8 bits. So the baud rate is just the bit rate divided by the number of characters that make up the character set. Another concept is the trade-off transmission speed and accuracy. And in engineering, an awful lot of time is spent evaluating trade-offs, because Mother Nature doesn't give you anything for free. So you're constantly looking at, well, what do I get? What do I have to give up in order to get something else? And let's say, for example, you want to be able to transmit a lot of data very accurately. Let's say it's life critical data. Well, you may not be able to transmit that as high a speed as you want, because if you want 100% accuracy, you would almost have to be at 0 bits per second. It'd have to be very slow, because it would take a lot of time to do the error detection and correction. Then as you speed up the transmission rate, where'd my mouse go? Oh, there it is. As you speed up your transmission rate here in bits per second, the accuracy or the correctly transmitted bits decreases. So you could get to a situation where, if you're wanting the conditions are such that if you're wanting to transmit at 600 bits per second, you get less than 75% of the characters right. Now, that's not, you just can't say that's good or bad, because it has to be evaluated against what you need. If you're just doing general chit-chat communications, that 75% may be fine. If you're wanting to do more accurate communications, then that won't be fine, and you'll have to determine where your correction factor is. And probably one of the most, well, it's not really well publicized, but an event, it's probably one of the biggest events in history, demonstrates this relationship here of transmitted accuracy and the bits per second. And there are other factors that go into this accuracy figure if you're designing a communication system other than bits per second. But in the Apollo 11 program, 11 was the first one on the moon. Neil Armstrong, when he stepped off the ladder, said, "This is what we heard was, this is one small step for man, one giant leap for mankind." And you're not old enough to remember it, but I was watching TV when that happened, and it was pretty neat, as you could imagine. What he actually said was, "This is one small step for a man, one giant leap for mankind." And that makes a little more sense. This always seemed a little awkward. And the reason was that the voice communication system was designed, I think it was at like a 98% correct value. So there was a 2% chance of losing information in the transmission. And that's what happened to the A. During the noise, which is a random event, took out the A, and this is what everybody heard and remembered. Okay, now air detection, there's a lot of different ways of doing air detection. Probably one of the simplest ways is a parity check. And the way that works is it blocks the data from the source subjected to a check bit or parity bit generator. So in this case, a 1 is added to the block if it contains odd number of ones. A 0 is added if it contains an even number of ones. So what would happen is the sender sends a byte of data here, 1001011, and it computes the parity bit by the number of ones. It's 3, so there's odd. I hope this works out. Yep. So it puts a 1 here at the end because this character has an odd number of ones. Then it goes through the transmission medium and it comes in, and this is what's received on the receiving end. 1 byte that's 100011. It has an odd parity indicator, and it is when the receiver computes the parity bits, it's also a 1. So if it's it'll accept the data if the parity bit is matches what he computes, and then it will reject it if it isn't. So that's one way of detecting a single bit error, say in an 8-bit or 16-bit word, or any number of bit words, I guess. It's just odd or even. So that's kind of a basic error detection. And when you go to set up some of these digital programs on your computer, you get into the COM setup, they'll be looking at whether it uses parity or not. So that'll be an option you'll have to select depending on the equipment you're using. Then there's and this gets a little more complicated. Here again, you're getting better information, but it's going to cost you a little more in terms of time and equipment and things like that, where you have a 2-dimensional parity check. And in this case, the sender sending these 4 words. Let's see where they stacked up. So this one's down here, this one's here, this one's here, and then this one's here. Each row has a parity bit. It's odd that those are all 0. I guess they're all even. Yep, okay, so these are all even. So each row has a parity bit, and then the columns have a parity bit. So it'll look at this one, this one, this one, this one. There's 3 1s, so it's odd, so it makes that a 1. And then it does the same thing to this column and these columns. So it's comparing column parities to row parities to show where a parity error might exist. And what'll happen is you can even correct it, because if you find out that this is the row that has the parity error and this is the column that has the parity error, then they just switch that digit. Now, when I say you do it, it's all automatically done in the control system for the digital streaming of information. But all this goes on pretty fast, and so this is just another level of error detection, and you can actually correct with it. And then there you'll see sometimes something referred to as a checksum. And what that is where the sender sends a character or a word like FOX. And let's say this is ASCII, which is kind of the standard, one of the standard codes for digital character representation. And the sending system will add the ASCII value of all 3 figures call that a checksum. So it just adds up the ASCII values of all these figures, determines the checksum, and then when it's received, the receiver does the same calculation and compares the checksums. And if they're both identical, there's a high degree of probability that the data was transmitted, was received as intended from the transmitter. If there isn't a match on the checksums, then depending on the system that's being used, there'll be some things that'll be done. A lot of times it'll be just ignore that last block of data, resend it. But that kind of slows you down too. So you'll see this, you get into FLDigi, for example, which is a digital mode we'll take a look at in a little bit. It has some modes where when it transfers text files, the sender will do a checksum for all the characters that are sent, and it'll be transmitted with the data. Then the receiver will receive the data, compute the checksum, compare them, and then it'll signal back to the sender if it needs a resend or not, or if the data was received properly. And there are different encoding methods. You know, you probably need to, there'll be questions on the test about this, but I think it's from a conceptual standpoint, it's just understanding that there are different ways of encoding these ones and zeros that are used for different applications and situations. One of them is the amplitude shift keying, ASK. You'll see this on some of the modes that you might happen upon. And here, the amplitude is increased to a certain level to indicate a 1, and there's no amplitude increase or no amplitude to indicate a 0. So that's how the ones and zeros are transmitted. There's another coding method called frequency shift keying, where it varies the frequency depending on whether it's a 1 or 0. And we'll be taking a look at, we'll be looking at, we won't be seeing this in the demo, we're going to look at it a little later. But you can see here, this is a 0, higher frequencies represented as a 1, 0, a 1. So the frequency is shifted in similar fashion the way FM is modulated with an analog signal. There is a frequency for the signal level. Here we've got two frequencies that we're modulating to indicate zeros and 1. Then there's phase shift keying. This is the one we'll be taking a look at shortly. PSK31 uses shift keying, and that's a situation where we're running along with this frequency signal, and then when we shift phases, it indicates we go from a 0 to a 1. So it'll shift the phase, because this sine wave, if we hadn't shifted, would have continued to go down and then come back up there. So we change the phase by 180 degrees, shift the frequency phase, and then there's a 1, and it stays a 1, and then we change it again, and then it becomes a 0. So that's a good way to communicate ones and zeros. And then there's differential phase shift keying, and I forget what that is. I've never really used anything that use it that I know of, but it does do, I guess, 2 different phases to represent a 0 and 1. Anyway, anything you can do that represents a 0 and 1 could be an encoding method. CW is a binary system in that it's either on or it's off, and it's the duration of the on period that determines whether it's a dit and a da, and then the dit and da combinations determine what the character that's being transmitted is. This is just kind of a subset of a lot of digital modes that are available. This is out of a program I have called Ham Radio Deluxe, and you can see all these different, for example, here's CW. This program can operate various means of CW. RTTY, that's the radio teletype, several different versions of RTTY that you can use. PSK, phase shift keying, 31's the baud rate. I think it's baud, yeah, or symbol rate, character rate, I forget what it is. But PSK 31 is probably one of the more common digital modes that are used for recreational ham radio. And then there's a lot of other modes. There's this Contestia, I think is how you say it, Domino, just all these different modes. And they're all used for different reasons because they all have different, fall on different places on that curve in terms of performance versus speed. Some are better in noisy environments than other. And then there's a lot of overlap too. So it's just a lot of different ways to do it. So specifically in RTTY, which is one of the first digital modes, because they would use the electromechanical teletype machines, just as they did on the telegraph lines. They could connect the teletype machines and send characters. Uses a Baudot code, I think is how it's pronounced, and that uses 5 bits per character. And this just shows the timing diagram that's the standard for RTTY. You really don't need to know much, if anything, about this unless you're designing equipment or software to use RTTY. But it does show how there's a structure to the transmission of the data where you have to indicate where it starts, the time where the data pulses are, indicate that we're stopped, and then go to the next character. So all the different protocols that are used to transmit serial data have these types of elements to it, and they just do it in different ways in different structures. I've had no experience with Amtor. It's evidently a higher density, data density transmission capability. I'm not too sure the specifics of that. Then here's the phase shift keying like PSK31. You can see here it's showing how you have the phase shift, and it changes the binary level from 1 to 0. Another phase shift, it goes back to 1. Here's another phase shift, so it goes to 0. So it's these shifts in phase that are used to indicate transition from a 1 to 0 and back. Amtor and Pactor, similar in that they have a data structure. I've never used any of them that I'm aware of, and but they do have, you know, here's the start, here's the data, here's the stop. There has to be some sort of handshaking that way in order to get the data set. We talked about these in the technician class, the handhelds and the base stations that use digital modes on FM, D-Star, DMR, and Fusion. And they all operate similarly in that there is a predetermined data structure and data handling technique for how they transmit data. So that's what I was talking about earlier when we talked about an encoder and a decoder. Those have to be matched. For example, if you tried to transmit on D-Star and pick it up on a DMR radio, it's not going to work because your encoder and decoder aren't linked together. They're not using the same protocols. So Now, what you'll see now that's kind of interesting is that they have the hotspots for digital modes on the VHF, UHF bands that will handle any of these. So you plug in your hotspot to your computer that's tied to the internet, and then you can use a D-Star, DMR, or Fusion radio, and the hotspot has the capability of selecting the proper, the proper structure, and so you can communicate that way. So that's kind of a neat thing. So this is about transmitting voice information on VHF, UHF. You get back here to these modes, you're interested like in RTTY and in PSK31, you're interested in transmitting text between stations. There's a third general area of digital communication that I think is pretty interesting. I think it's, I find it very intriguing because of what it can do for you. But it's essentially email without the internet. Now, it's set up, it's called WinLink, and it can be set up to do email with the internet. And the way that would happen, if you're doing it with the internet, is a station would be running this WinLink program. And if we have time, I'll pop it up on the radio's computer. And it'll transmit by various modes an email message that goes through. It could either be HF, you can also do it with VHF and UHF, but it'll transmit the information wirelessly with RF to receiving stations that have HF or VHF, UHF receivers. So they're receiving the email and then tying it to the internet. Now, the thing that makes this, in my mind, my opinion, so interesting and powerful is that you could also operate it so if the internet's gone, you can still send emails peer-to-peer in these from the stations. So you can send an email from this station to this station and they can respond without any use of the internet. And I think that's an ideal way for emergency communications, particularly because if you're wanting to transmit, say, a block of information, maybe a supply list needed at a hospital would be an example, let's say, or a patient list or something like that. You can generate that text file at the location on the computer, and then you can attach it to the email message and transmit it to another station, even if the internet isn't there. So it's just a pretty neat mode of operation. A lot of changes going on. And the thing about all these digital modes of software, there's a lot of free software available that will do it. There's some software you can purchase, but the free software is extremely powerful. So all you need to do is put the effort into getting things set up. So here's an example of what I was talking about. They use HF Pactor. There are some other modes that can be used where you can do direct peer-to-peer. You can transmit to these remote monitoring stations that instead of using the internet, it'll retransmit to another monitoring station that will transmit the email. So it's very flexible and dynamic, but it works extremely well. Okay, we mentioned concern about duty factor, duty cycle. Most of the digital modes operate at 100% duty cycle where the transmitter's on. Because if you think about it, let's say you're using frequency shift keying. FSK. So all you're doing is changing the frequency, but that means that you have a constant amplitude the whole time. So your amplifier is on the whole time. So if you're set up to run 100 watts and you run a long time signal of frequency shift keying, it's going to run your amplifier at full load. Whereas with, for example, a single sideband signal, because of the variations up and down of your voice, the amplitude goes up and down. So your average on time is maybe 30–40% if you're set at full peak envelope power. So the digital modes generally run lower power. You don't necessarily need that much power because the digital modes tend to be very good at the low signal processing. And then as pointed out here, where was that, on CW, the transmitter's off between DITs and DAWs, but it's still a pretty high duty cycle. Single sideband, like I mentioned, you only reach the peak power for short periods. And then FM is constant power mode, so the signal's continually at full power when the transmitter is keyed. So it's just something you need to be aware. For example, I have a 100 watt transceiver, and I generally run single sideband at 100 watts and have no problem with the radio heating up because I don't talk that much. But on digital modes, I generally run it at 50 watts or 25 watts. So right there, I'm cutting my duty cycle in half, or the power consumption in half. So it keeps everything nice and cool. Now, I didn't notice on when we do POTA and Judy's on the air, the fans on the transceiver kick on because she keeps that press to talk button down an awful lot, and she's constantly talking. So you can get conditions where single sideband will have a little higher duty cycle, but it's not bad for the fans to kick on because they're there to cool the transceiver down a little bit. This is out of the book, talking about duty cycle. As you use this more, you'll probably need to know some of this for some of the questions, but it'll make sense the more you use it. There's been a big, I wouldn't call it revolution, but a big breakthrough in a digital mode, several digital modes that ham radio's been using the past few years. And what this is a graph showing the percent of modes used by ham radio operators, where this blue line is a phone or single sideband, and you can see it kind of declined over the years and took a pretty healthy drop here starting about 15, 16. CW, similar, it drops off, really kind of flattens out here. And what happened was the fellow came up with this weak signal mode called FT8, and there's some variants of this that has just taken the ham community by storm. And what it is, it's a method of decoding digital signals where you can actually extract the signal if the signal's below the noise floor. And it's done mathematically. And the thing I find interesting about this is when I was studying in school, and this was 50 years ago, we were studying this stuff, but there was no way we could do it. It was all abstract theoretical on the blackboard type stuff because it took pretty powerful computers to do these calculations. And obviously they weren't that available 50 years ago. The government and the military had them when we were using this. But now here I am 50 years later with a desktop computer doing the same thing that I studied back in school. And it's kind of like in the Twilight Zone. I step through a door and all this stuff's going on. But what it does is it has really taken the ham community by storm where you can see this FT8 curve starting in 16. And this graph is only good through 19. It continues to be this popular, if not more popular. And people do an awful lot of QSOs on FT8. And this is an example of, this is a website called PSK Reporter. And the way this works is that hams that are using certain software packages can report the signals that they're hearing on different modes, whether it be FT8 or PSK31. And you can get a plot of all the hams in the world that are connected to this PSK Reporter system that are transmitting and receiving signals to where they're going. So in this case, it looks at all the bands for signals that were sent by anyone using FT8 over the last hour. So these are all the signals, and typically there are thousands of them on all the bands going on all the time. There's always traffic on FT8 and FT4 and some of these other weak signal modes. But this is, there's a lot of controversy on this because some of the old hams say, well, if this isn't ham radio because you're using computers and you're really not talking to anybody. What I like about it is I can use it to see how my propagation is doing in real time, because you can set this up to where I put my call sign in here and it'll show me all the people that have heard my transmissions, who've heard my call sign, and I can see where my antennas are getting me around the world. That's the kind of thing I like about it. And this is what the screenshot would be of an FT8 session. And this, all this software is free, but essentially what it has, let's start here. This is, now let's start here at the, this is the waterfall. And where this is on the frequency spectrum is if we're on, let's see, what are we on? Okay, we're on 20 meters. And the frequency that we start on is 14.074. And that's an agreed to frequency that everybody pays attention to. So this point here on the band scope is 14.074. This point right here, 2200 hertz higher, would be 14.062. So it's just 2.2 kilohertz above this signal. Now the actual band width is 3 kilohertz, which is the same width as a single sideband signal. So what we're doing is we're taking the bandwidth of the single sideband slice out of the frequencies, and then all these are individual conversations between stations. Now all these communications are decoded down here in this window. So you can see here, for example, this line is CQ, the guy's call sign is N7XG, and CN84 is his grid square. So he's requesting people to contact me. And here's one I did, CQ KF0UR, which would be this call right here. I'm tuned to that frequency up here, wherever the green thing, oh, right here. The green is where I'm listening. So I hear him, and then I respond by sending this signal. He's calling CQ. I say KF0UR. This is K3SKS, and I'm in FN01. And I had to call him twice for him to come back to me. The red indicates his transmission. He comes back and he says K3SKS. This is KF0UR. I'm reading your signal -05 dB. And then I send back to him that I'm reading him +7. So that's the signal strength that the program picks up. And then he came back to me and said, Roger, Roger, 73. And then I said 73, and the QSO was done. So that was a contact between two stations. And it was all done pretty much automatically once we got it started. So this is the band scope for that 3 kilohertz signal. This window shows the decoded signals, and it shows you the call sign, the signal report, and where the signal's coming from. And if it's a CQ call, it'll be green. And so you can spot the stations calling CQ. So it's kind of fun. It works extremely well at night. Just about any time of the day, there's a lot of people on. But that's called FT8. And once you get up and going on your single sideband station, then that might be one of the things you'd want to get going on. And there's a lot of help around to help you get all that stuff started. So it's not as well. It's a little complex, but not as bad as you might think. It's pretty doable. And then this is an example of the QSOs I logged on, it's been 2 years ago now, using FT8 one day. I just wanted to see where they all were. And see, I was able to get to Australia, New Zealand, over here, Japan, Alaska, down here in Antarctica. This was a scientific station down there, a couple stations in Africa, and pretty much covered the Western Europe there pretty well. Okay, any questions about any of that? I'm going to get into another weak signal thing that I'm playing around with right now that I find kind of interesting. Have I lost you yet?
No real questions. Just looking forward to updating my radio and all that stuff.
Oh yeah, I tell you, this is where the fun starts. The technician level's fine to get started, but there's so much to do on HF. That's when it really gets to be a blast. And there's so much you can do. You kind of pick an area you want to go work on, and you can just have a real good time doing it. So I'm tacking on this weak signal propagation reporter. It's a part of that FT8 package, and I've been using it the past couple of weeks, trying to understand propagation during the day and evening and night times. So this was something I put together. In fact, you may have got an email with this attached to it. But it's a mode similar to FT8, but there's no exchange between stations. It's just if a station hears your call sign, they'll report to the Whisper server, wherever that's located. And if you receive a signal and identify the call sign, it's automatically reported to that server. And the way I set it up, for example, is I was interested in 20, 40, and 80 meters. So you can set up a schedule that, and the way I did it, I set it up 50% of the time I wanted to transmit and 50% of the time I wanted to listen. So the program takes control of your radio, and it'll transmit a very low power, very tight frequency signal for 2 minutes. And then all around the world, any stations that hear that will report it back to the Whisper server. And then you'll listen for 2 minutes. And then you'll hear all the different call signs. And then these are what your computer sends back to the Whisper server. So let it run for several hours. Oh, this is, I'm not going to play this. This is a pretty good video that explains all this from this Dave Kassler. If you're interested in it, you can click on that link and go see his presentation. He gets into more detail on it. But what I was looking at here, after this test, I ran it on 29th. I was using my InFed half-wave 8010 antenna because that's a multi-band antenna, so that the program could switch the radio, and then the antenna would be able to transmit and receive on whatever frequency the radio's switched to. All my dipoles are manually adjustable, so I couldn't have used them in this test. So this was a 20 meter. This was from 10:56 to 11:24 UTC, which is 4 hours ahead of our time right now. So this was about 6:56 in the morning to 8:30 or so. So that'd be an hour and a half. And on 20 meters, these were the stations that heard me. And a lot of them into Europe, another guy in Antarctica, here in South America. But then I did it, let's see, I have to move something out of the way here so I can see it. Then in the afternoon on 20 meters at 13:50, well, I guess it wouldn't be the afternoon. So I'd be 11:50, be close to noon. The propagation changed such that more stations heard me across the United States, over into Europe. So the propagation had improved from this point in time to this point in time. And then I also did it for 40 minutes or 40 meters. And you can see this was in the morning, and on 40 meters even, I was getting down into Australia and New Zealand with the signal up into Alaska. But then by the right before noon, then the propagation died down. I was barely able to get out of the United States. There were no stations outside of this shot here that could hear me. And then on 80 meters, 80 meters is generally a regional band where in the morning, that morning time period, all the morning sessions were at the same time. For 80 meters to get to Hawaii, New Zealand, and Australia is pretty amazing. But then by that 11 o'clock time, it slowed down to where I was getting what would be generally a typical 80 meter distance pattern. So that's Whisper. Okay, so now I'm going to try something. Oh, it looks like the bands just went dead.
Steve,
Yeah.
your YouTube shooting class.
I'm going to pause. Judy's asking me a question. I'm going to pause the video here if I can find it. Pause recording. Okay, got the recording back on. So I'm going to try to switch the presenter to my other computer. See how I do that. Okay, look at participants. Oh, okay. So I'm going to change the host to the other computer. And let's see, where might that be? I think I'm going to pause the recording while I'm doing this, if I can find it. Okay, we're recording again. And what this is, I think might have seen these two windows before. These are the windows in the control program for my HF rig. And this is the band scope. And this is the radio control. And this is a program called FL Digi, which is a free software package we're running digital modes. And just as an example, these brown tabs here are different digital modes that you can use, and there are a lot more than this, but these are the ones that I typically use, so I've got them in a shortcut key. So the way this is set up is this band scope here is very similar to what you saw.
Well, like I
on
mentioned, this is
FT8.
the shooting range safety
Sorry.
course. It's for the assistant range safety officer.
I found it.
I had a hacker, maybe that was it. So this is the band scope where the frequencies are that we're going to try to see. This section here from 0 to 2000 is the same section on my radio from here, which is 0, or the 14.070 to 2000 to here. So what I'm looking for here are signals that I can decode, and they should either show up here on the radio or here on this band scope, because it's looking at the same part of the frequency. And it's, what time is it? It's 2 o'clock in the afternoon. Typically not a good time for PSK 31 for propagation and just number of people on the air reasons. So I'm going to change to 40 meters. See if that looks any better. So that changed to 7.070. The PSK frequencies typically end in the 7.0. So 40 meters is 7.070 megahertz. 20 meters would be 14.070 megahertz. So let's go back to 7. And you can see that my program is controlling the frequency of the radio. And I don't see much in the way here of PSK signals. So I think what we'll do is I'll close this and we'll jump to FT8. We'll give that a shot, because I know there's signals there. I saw them. Let me pop this up. Okay, so this is the screen we looked at earlier, and why aren't I seeing anything on 40 meters? Oh, because I haven't set the frequency right yet. The piece of equipment that causes me the most problems in the shack is the nut that turns the knobs. So I go from 7.070, I'm going to select the FT8 frequency, which is 7.074. There we go. Now, if we look at the band scope on the radio, this is the FT8 band. And the 0 is 7.074. And then we go 3 kilohertz up to be 7.077. Each of these traces is a signal that's being received. And you can see they all start and stop at about the same time. It's set up on 2 cycles. The first cycle is 15 seconds where somebody's transmitting and you're receiving. Then the next 15 seconds, you transmit and they receive. So you can see that's what we're seeing here on this band scope, these multiple stations transmitting and receiving. So this band scope here is of the same frequency section as we have here, but it's spread out so you can see it a little better. And there's not a lot of signals going on here. I think I'm going to go to 20 meters and see what that looks like. Okay, so this is on 20 meters. It's 14.074, and you can see we got a lot more activity here on 20 meters at the time. But they're running on the same 15-second cycle. So let me see if we can get a QSO going here. I'm going to turn on this other program that will show me the call signs of the people that are transmitting. There's our band scope. And then this window should show us people calling CQ and our other stations transmitting. Okay, here's one in Missouri. I think I'll go for an easier one. Texas. I've got a direct pipe into Texas. So what I just did is I clicked this box and I'm sending out a call to this fella, K5BEK. And we'll see if he'll come back. So the yellow is my transmissions. He's still calling CQ. So I send back another one. This is all being done automatically. So I'm sending a response back to him, telling him my call sign and location. I don't know if you can hear those tones or not. I'm going to turn them up. Okay, it turned red. That's his call back. And he's telling me that he reads me at minus 16 dB. I roger him that I'm reading him at minus 6. You can see all this going on up here. Now his signal, my signal's right in this section here on the band scope. That's the frequency we're at. Okay, so he came back and said, Roger, Roger 73, and I sent him a 73, and the QSO's done, and I've got it set up to automatically log the exchange. I'll just click OK, and it'll put it into my log file. So that's how a QSO goes in FT8. Now, I saw someone from Finland. That might be a tough one to get. Well, there's Spain. Let's try getting Spain. So that's the fellow in Spain's CQ call. Here's my response to him. I wouldn't be surprised if I don't make it. The afternoon's not the best time for propagation. He's still calling CQ. Maybe he didn't hear me.
So now once your computers talk to each other and you figure out all that information, how then can you just switch over to voice?
Yeah, you can. You could. That would be called doing a QSY, which is changing frequency. Now, all of this is done. All the digital is done in the CW portion of the band on all the bands.
Okay, all right, I got you.
So if you wanted to go to voice, you just make an agreement. Okay, let's go to, say if you're on 20 meters, let's go to 14.250 plus or minus 3 to have a little range, and then you would transition to the voice part of the band. Now what I've done, I've got, let me shut this down so I can open up another program. I've got a program called Ham Radio Deluxe, which does digital modes and a lot of other stuff. It was you had to buy it. I think it was around $100. But one thing that I can do with it, let's see, let me move this over here. And as far as I'm concerned, it's one thing that makes it worth its money. I've never tried this with both of them going on. Now let's move this. Yeah, move this here. Just bear with me. Okay, so here's my radio control that the way I've got it set up, it goes through my local area network and controls the radio. This is Ham Radio Deluxe radio control, and it controls the radio through the USB ports. Now there's a capability in this Ham Radio Deluxe that's real neat, the macros. And what you can do is you can say if you're on, right now, we're on FT8. And what that means is we've got a setup of upper sideband. Here's the frequency. The power should be at 50. There's a bunch of other different settings that you have to do to set it up to run on this FT8. And what Ham Radio Deluxe allows you to do is once you get it set up, you take what's called a snapshot. And this is a snapshot, for example, here that I had it set up for FT8 on 40 meters. And then I've got one for PSK 31 on 40 meters. Then down here are my single sidebands. So let's say what you were talking about, if you wanted to talk to somebody, and I'm sitting here on this one now, FT8 40 meters. Well, this is actually 20 meters. That's how the radio's set up. If we decide to go to 40 meters, I can go down here and click on this, and it changes the radio setup, power, filters, just about everything changed. So the way I had it set up to go to 40 meters in single sideband up in the voice range. And say if I want to get back to FT8 on 40 meters, I just click back, and there I am. So there's other things I've got it set up to do, but this is one advantage of having the computer hooked up to the radio. You can save your settings, back them up, and easily go from one to the other. While we're here, let's take a look at the digital mode setup. We were looking at FL Digi. This is what Ham Radio Deluxe's digital program will look like. Now, the reason I've got both of them is that I started with Ham Radio Deluxe because it has a lot of other neat features like satellites and that kind of stuff. But when I got into the emergency communication, most of the emergency communication is done using FL Digi. And there's a suite of programs that go along with FL Digi that are pretty handy for data communication. Okay, so this is the screen, Ham Radio Deluxe. I'm on the wrong frequency, so let's go to, this is the FT8 frequency, so I'm going to select the PSK 31. Now we're looking at PSK 31 to change the radio to 7.070. Now what this is that same band scope that we saw going across the screen on FT8, but it's on its side here. So down here is 7.070. Help if I change my antenna. See if that gets us some signals. So the signals, if I get PSK 31 signals, I'm going to start seeing streaming across the screen here. And I'm not seeing any. So I'm going to go to 14 meters or 20 meters, 14 megahertz. See if we've got some signals there. it's looking pretty dead. Of course, this happens anytime you're wanting to show somebody. Let's try 80 meters. You never know. I don't have high hopes for it, but. And we're not seeing any signals there. Let me go back to 40 meters. So this is kind of the broad spectrum monitor that you can use. And when you actually go get a signal, you can go to this window. This is that same spectrum we were looking at, but it's rotated horizontally now. And you would see the signals going down here. The way this page is set up, this black screen has all the signals, the text from anybody you're receiving, and anything you send. So this is the send and receive window. This is the transmit window. So I'm going to call a test CQ just to show you how it works. Okay, now when I hit the auto button, it'll transmit it. It's going to send CQ. This is my call sign test, and then I'm done. So it'll as it's transmitting, you'll see those characters appear up here. Oh, let me send that. So that's what somebody would see at their station if they were working here, looking at my signal and then tuned into it. Now you look down here on this waterfall, and this is what a PSK 31 signal looks like. I'll send it again. See, that's the signal. Now, if that was an incoming signal, I would put this right here and click it, and then I'd be monitoring that frequency. Well, I wish we'd see a signal. This is kind of like fishing with no. Ah, here's somebody. Okay. You must have called the CQ. Might have missed it. You notice the signal's not as clear and sharp as the one I sent out because I've got the, receiving a signal is where you start picking up the noise and things like that. See if he'll come back. Here's a signal. Let's see what this one is. Let's look on that. Okay, he's calling QRP, which means low power. And I believe that's under 10 watts. So he says that, and he's KD9LAI. And he wants somebody to acknowledge. Let's see. Let me get his call sign. I don't have the logbook started up. I'll just try it this way. Oh, typing on the wrong keyboard. That's trouble with running two computers. So his call sign is KD9LAI. Okay, he's calling CQ again. Good thing I didn't send that because I can't type. There we go. Okay, so I'm going to send it to him. So he's asking for a call, and I'm going to respond to him. Okay, I'm gonna tell him where I'm at. Um, You can see it's crossing out the text. So that's how you do the keyboard to keyboard exchanges. And there are ways, like some of these they're called macros. And that's over on the other, open up on the other screen. But what they do is it's just canned responses. Like if I wanted to send him he's doing POTA, Parks on the Air, so I've got to tell him my wife is